So today's topic is random variables, and let's begin with it. It is one of the most important concept in probability theory, independence of random variable. What is independence? Independence is a simplifying assumption used throughout the statistics, machine learning, Bayesian inference, graphical models, in deep learning also. So by the end of this presentation, you will understand not only the mathematical definition but also when it applies and when it does not. So let's first build an intuition about what independence actually means. So independence does not simply mean two variables are unrelated. It means one variable provides absolutely no information about the other. For example, if I pair two fair coins, the outcome of one coin tells me nothing about the other. Now compare the same thing with the variables like height and weight. Knowing someone's height gives us information about their likely weight, so those variables are not independent. Now, independent is the extreme case where there is no information shared. So now let's see the mathematical definition of it. The formal definition is just simple. Two random variables are independent if their joint probability is equals to product of their individual probability. So instead of computing the joint probability separately, we can simply multiply the marginal probabilities. And if the probability of, for example, if the probability of rain is zero point 0.3 and probability of carrying an umbrella is zero point 0.4, then the joint probability will be 0.12. So, uh, moving on forward, the independence equivalence matrix. Here we see different mathematical forms that all express independence. Whether we use joint distribution, conditional probability, or expectation, they all reduce to same idea, knowing that one variable never changes the distribution to other. Now, one of the most important identity in this given slide is that probability of x given y is equals to probability of x. It means learning y does not change our belief about x. Okay. Now, moving on forward, here's a quick way to detect dependence without doing calculations. Look at the shape of where probability exists. If the valid region is not a perfect rectangle, the variables cannot be independent. Now, seeing this triangle, in this triangle region, once x is shown, x is known, and y becomes restricted. That means knowledge about one variable automatically tell us something about the other. So, a non-rectangular support almost always indicate the dependence in two variables. Okay. Now, moving on forward, the factorization test in action. Okay, now let's apply the definition to actual example. So here's the question. In first example, the joint probability is equals to the product of marginals. So therefore, the variables are independent. Now in the second example, you can see the factorization fails. Why so? Because multiplication is no longer reproducing the joint distribution. The variables are dependent on each other. That's why. Now moving on next slide, the engine of statistics. This is like one of the most common assumption in statistics is like it stands for independent and IID, which stands for independent and identical distributed. Independent means samples don't influence each other, and identical distribution means every sample comes from same probability distribution. Examples like tossing a fair coin repeatedly and random sampling from a population. Many machine learning algorithms assume that training data is um, independent and identically distributed. Now, conditional independence. So, conditional independence is like a bit different. Two variables may appear dependent initially, but after we know a third variable, they become dependent. This is what it actually says. Now, see this Z here. Let us take an example first. For example, ice cream sales and uh, drowning death seems related, right? But once we know the reason or temperature, the relationship disappears. The hidden variable explains both. Okay, there was a research done in America, I guess, that says that where the ice cream was eaten on a day, on a specific day, if ice cream was eaten too much high, the murders also becomes high. These things become like there is zero correlation in relation in between these things, right? But if we see like once the third variable comes, means once the weather comes, means the day was too hot that people also died, and ice cream melted fastly. So that's why people ate ice cream more. अरे यार, but I spoke. It's okay. Leave. Now the idea leads directly to graphical models. Now what we see is like X influences Y influences Z. Once Y is known, X and Z becomes independent. You got my point. Like one common cause affects two variables. Knowing the common cause removes the dependency. Here is like two variables influence here like two variables influence one common effect, and conditioning on that effect creates dependency. Now this is the last case. This last case is often the most um, counterintuitive. So we move to next slide. Like false dependency means correlation does not always mean causation. This was the thing I was trying to explain 2 minutes before. Correlation does not mean causation. Sometimes variables appear dependent simply because of the hidden factors which we don't know. If we ignore these hidden variables, like you can see this graph, if we ignore these hidden variables, we may incorrectly conclude that one variable caused the another. Now here comes Bergson's paradox, which says Bergson paradox is basically an example of collider bias. So it says like two independent variable become correlated after selecting only a certain subset of data. Okay, examples like imagine selecting only students admitted to a competitive university, and in academic ability and extracurricular achievements, these may appear negatively correlated if they are independent in general population. Means like what we can conclude is like selection itself cannot can introduce false relationship. Okay, now, marginal versus conditional independence. Okay, so these two concepts are like often confusing. Marginal independence consider the variables by themselves, and conditional independence consider them after another variable is known. Now, see the diagram. A pair of variable may be marginally dependent, but it's conditionally independent, and reverse is also possible. Now, independent pitfall, okay, but where we can make mistakes. Let's see. Before claiming independence, we have to check these common mistakes which we make sometimes. Assuming that zero correlation implies independence. And second is like ignoring hidden variables. Third is like ignoring the support shape. Fourth is forgetting conditional dependence. So independence is a very strong assumption and it should be verified carefully. Okay. Now, why we are studying this? What is the need of this independence topic in our machine learning architecture? So, this independence assumption appear throughout our machine learning process. So, like Naive Bayes assumes that features are conditionally independent. Bayesian networks explicitly model conditional independence. Now, hidden Markov model also is a thing, like which rely on independence assumption over time. Then there is a dropout in neural networks. We use this, in which encourages the independent neuron behavior during the training time. Now, these assumptions simply simplify the computation and make learning very much easy. So, what are the takeaways which we did? First thing that independence means completely absence of information sharing. Okay. Second is always check the support shape and hidden variables. And then conditional independence is different from marginal independence, that we have to remember. And what are the differentiation factors? We also have to remember those. Now, independence assumptions are central to modern machine learning. So remember this also. So that's all for this video. I tried my best to explain this topic. We'll see you in the next video. Bye bye.